Is the low frequency output resistance R naught in ohms if the amplifier shown is at a 27 degree C with RC, RE, RB, IC, beta, and VT. We're going to use a shortcut approach, and this is discussed in the notes, linked below the like button in the description. So the first thing that we're going to want to do is go on to page 132. And the reason why we need to go here for the beginning of any problem like this is because we need to identify what kind of emitter amplifier it is. So we can identify our emitter. Looking at them, we can see it is going to be a common collector amplifier. Do not get it confused with the common emitter amplifier. They're both very different, and there are two different equations. So after we find that out, we can look up common collector, and this is going to be our amplifier. We can look at these notes right here. And although it looks a little bit different than what it is right here, this is just the alternative form for it. So scrolling down, we are going to get these notes. That's how we would find this. And we want to find our R naught. So writing this out, we know that our R naught is approximately equal to, we have 1 over RE, this is resistors in parallel, plus, now we have this first part, and we have this second part. And this second part is going to be a little interesting. We want to find the low frequency output, right? So if it's low frequency, our RC, the output, because this is the output here, is going to be much less than our R naught. And with that, we can see that this is not going to be in the picture. Really, our R naught is going to equal to infinity, so we have RC over infinity, and this is going to give us a 0 here. And then we would just multiply this by 1, which gives us nothing. So when we put it in the parallel form for our resistors, we can just put the denominator in the numerator. So we are going to have our beta plus 1 divided by our R pi plus our RB. Now, this is going to be raised to the -1. We need to find some things. We know a lot, but we don't know our R pi. So we need to solve for it. Now our R pi is going to be equal to, if we look back here, there are a few things that we can set this as. So looking at the controlled current source, we've used this earlier, we can take this and use it inside of here. So we know that our R pi is equal to a V1 over our IB if we rewrite this out. And our IB, if we rewrite that, is going to be equal to a I over our beta. And our V1 is going to be equal to a I over GM. So that means that our R pi is going to be equal to a I over GM over I over beta. Now we can get rid of the i's because there's an I in the numerator and the I in the denominator, so we can multiply the top and the bottom by 1 over I for each of these, and then we're going to get a 1 over GM over 1 over beta. So we can multiply the numerator and denominator by beta, and we get that our R pi is equal to beta over GM. Now our beta is 19. We don't know our GM, so we need to now find our GM. Well, GM is equal to a I over V1. And we can actually rewrite this, and we can rewrite this as a IC over VT. So this is going to give us 328 microamps over a 26 millivolts. So that is going to be for our GM. Now all we need to do is solve for this and plug in our values. So our G of M is going to be equal to approximately 12.62, and this is going to be in millis. So this is the GM, and we can plug this into here. So we have 12.62, and this is in millis as well. So our R pi is going to be equal to approximately, this is not exact, 1.51, and this is times milli, or no, not milli, times a kilo. Because when we have a milli in the denominator, if we want to put it to the top, the equivalent is a kilo. So we have R pi of 1.51, and this is in kilo ohms. So now we can take this and plug into here. We know everything else. Our RE was given to us. Our RB was given to us as well, and our beta is given to us also. So plugging all this in, we're going to get an answer of approximately 69.53, and this is in ohms, and that's how we would go about solving for this problem.